Okay, let's start with lecture number 2. First, a couple of announcements. As I said, there's the lecture slides and a quick reference guide. I highly recommend the quick reference guide because you will need it for the midterm too. And it's like the one thing that is allowed for you to have during all the midterms that we will have. Lecture slides, this will be the last time I print them out. I will try to post them the night before the lecture, so it could be towards midnight or something, but in the morning of the lecture they should be online on the website itself so that you can print them out. All right, a couple of things I forgot last time. Graduate students, we do have some graduate students, and you are having a little bit more work than undergrads. So the two requirements that I have is that you will give a in-class presentation of an embedded system of your choice. More details will come a little bit later in the course. And the other one is that your project is supposed to have a little bit of a research component to it. So it's not just building a system, but it has to have like some research behind it that has to be done using this particular system that you're building. There is no textbook, but a good reference is the Definite Guide to the ARM Cortex-M3. That's this book here. It's a really nice book. There's a lot of the examples that will come in the lectures are actually out of this book. It's a very nice overview of the Cortex-M3 itself, but I don't make it a requirement because most of the information will be in the slides that we have, and there is a lot of different handbooks online that are for free. We will cover some of them in here in this particular lecture. Labs, you can get card access. If you don't have card access, you can get card access to the digital lab by filling out one of these forms that sits there, and then they will give you access to the lab itself. It's 24/7, so you can go whenever you want and use the lab, unless, of course, there's another class being taught in there, so they have always preference to you. You can pick up the hardware that you're using at MEB 1381 starting this afternoon. So you have to sign a little paper that you received your hardware, but then you have the hardware checked out for the rest of the semester and you can work at home if you want to. All the software that you're using for programming the system is online. It's free. It's not free as in open. It's like free as in beer. You have to get a license for it. It's a 1-year license, but the license itself is free, so you just register online, download the license, and then you get all the tools that you need to program your A2F eval boards. Homework 1.1. I realized it's a little bit crazy to have this due today, so it will be due on Monday, so you actually have the whole weekend to actually put a little bit more time into the schematics and figuring out, because it is an important thing, like to read these data sheets. But at the same time, I want to take some fear away from you. This is not the break-all homework. You don't have to come up with a super amazing system. Like, it's really good enough if you just have a little microcontroller, one LED, that's good enough, right? Like, the point of this exercise is that you use the software, you go through the steps of actually making your embedded system, because it's a huge advantage later on. You actually know how this works because you have done it before. All right. Minute quiz. Heads or tails? Head or tail? Head? All right. If it's head, we don't have a minute quiz. It's tail. Trust me, it's tail. Can you help me? Just keep the extras, we will collect them later. Everybody has one? Yeah. All right, this should be very easy. Basically 2 words can answer the whole thing, so you don't need to have a big sentence or anything. Rules, closed book. It's 1 minute for this one. Go. There are multiple answers, so. Multiple possibilities. 30 more seconds. Ten more seconds. All right, pencils down. And let's collect the bearings. Put them into the aisle so we can back up. All right, what's the answer? Yes. What? What do you think? Professor Schmidt? Maybe. No, not really. No, what's the answer? Like, what did you guys write down? Cost, inexpensive, size.
One process in one package.
Technology, right? Advances in technology. So lots of different answers, possibilities. Sorry? Yeah. Works too. That was an easy one, so it will probably get a little bit more difficult through the rest of the lectures. All right, a quick review for homework 1.1, a couple of pointers I want to give you on the way while you make your schematics. You might hear words like decaps or bypass capacitors. These are capacitors that you put onto the power rails of your microcontrollers. Basically, they help smooth out fluctuations on your power lines for your microcontroller. And once you lay them actually out, so after putting them in the schematics, it doesn't really matter where they are. You try to put them physically too close to where you really want them placed later on your PCB, because that just makes it easier to read a schematic and compare it with your PCB itself. But on the PCB itself, so in reality, you really want them as close to the power pins as possible. So not like having a long line in between your bypass capacitor and your microcontroller, because that's an inductor again. So you have an introduced problem. So you want these bypass capacitors as close to your power lines. There is a document online on the website link that's called the PCB design tutorial. There is a very good section there that's called good bypassing. So have a look at this section, or actually at the whole document, because it's a really good read. Schematics should be clean as possible, so there shouldn't be a big mess. And yes, I understand it's an art, it's something that you learn over time. So if I make a lot of notes on your schematics while correcting them, don't be afraid. I'm really just trying to help you so that you can improve over time. One of the things that I see all the time with beginners of schematic designs, they rotate VCC and ground around. Do not do that. It really confuses everybody that reads a schematic. VCCs always go up, grounds always go down, because it's basically like the flow. VCC comes from the top, power goes in and goes out on the ground. So don't try to have a ground symbol upside down. So if you see the symbols, VCC goes like this, powers go like this. Never ever have one of these signs that go like this. It's really confusing. All right? So this is a big no. Again, it's electrically correct. It's just not good practice. Footprints. There are a lot of confusions about footprints. We have a couple of discussions already online. Every company has slightly different names for the exact same footprints. TI is one of the very bad ones because it's like really confusing sometimes on how it works. So try to choose, actually I have another slide later on, try to choose a TSOP package. It's probably one of the easier ones to solder on. QFNs are acceptable. I will show them in a second too. So that's quad flat pack. TSOPs are leaders. They have like small little leads on the end. So try to use a TSOP package if you can. Yes?
So when you're picking out samples on the TI website, there's a package called.
Yes.
Usually say TSOP, it's like NAND or EDA.
It's possible. Look at the discussions. There has been a link posted to TI's conventions on what TI calls which package. Use that link. It's very helpful. And I agree. I mean, even if I go back on TI's website, I have to look really hard to figure out which package is what exactly in standard notations. All right, LED circuits. Who knows how to design a LED circuit? Yes, yes. Some of you. Who has absolutely no idea? It's fair enough you can say yes. I had no idea a couple of years ago either. So, all right. This is an LED circuit. It's a very simple LED circuit, right? An LED lights up when current goes through it. So we have a little power source here. We have current, lights up the LED, right? So how does this really work? Or how do you dimension how much light is shining in this thing? Resistor here, right? This resistor limits on how much current can actually flow through this circuit, right? So what we know is we know the formula U is equal to R times I, right? Or V, actually, sorry, U is 0. V equal R times I. Now, can we just take this V, this I, and this R, and we know the current through the LED? Not really. The problem is there is a voltage drop over the LED. Now, even more complicated, this voltage drop over the LED depends on how much current is flowing through your LED. So this makes the whole equation a little bit more complicated. If you look here on the right-hand side, these are two graphs. And you find these graphs in the data sheet for your elements. So if you go, for example, to this particular data sheet, this is from a Osram 0603 LED. That's actually the LED that I'm using in that tutorial video. You can see that the forward voltage drop increases the more current. Is this right? Yeah, the more current that we are using. At the same time, we have more light. More light up with more current that's flowing through it. So now we have to make a design decision, right? We want to say, okay, how much light do we want? So you go here onto the light. You find the amount of current that you need through the LED. You go over here, search for that particular point, and see that you now have a forward voltage drop of 2.7 volts. Right? So with the amount of current that flows through here, you have 2.7 volt drops over this LED, and the rest will be the voltage drop over the R. So now you have to dimension your R for this voltage that's dropping over this resistor in order to get the particular current that you're interested in. Did that make sense? Yes? Okay. So now you know how to dimension your resistors in your schematics if you have LEDs there. So find an LED that you're interested in, that you want to use these figures, get a certain amount of light out of them, dimension your resistor, and you're good. Another question that might come up is, what's a BOM? It's a bill of material. So the bill of material basically tells you what all the components are in your schematics. It's used to order your parts. So on your board, it's probably not very complicated, but imagine you have a very complex system. You need a bill of materials so that somebody from purchasing, for example, can go and actually order your parts. Again, back to the packages. So use the TSOP packages if possible. Yes?
Can we use dip?
You can use dip if you want to, yes. Now, somebody else would inform you that dips are not supposed to be soldered into PCBs, but let's just go with it for now. Usually for dips, so dips are these the ones that have like very big leads on the outside, very simple and easy to solder. So usually you have a socket that actually solders onto your PCBs, and the dips actually go into it.
If we actually do use dip, who's going to drill the holes? Us or
the manufacturer? Yes. No, you're not drilling anything. So that's actually what you're doing in the layout design. So once you design your PCBs, you tell where you want drill holes, how big they should be, how much copper there should be around it, and the boards will come back like that. So don't worry about that part. All right. Absolutely do not choose a BGA or an LGA package. They are really hard to solder by hand. It's possible, but it's hard and difficult to do. Yes?
What's the purpose of this board? Do we use this board in our final project or just for practice or is there?
You won't use this board for the labs. So no, the purpose of this board is really just to go through the motion of doing it. You might be later on using them for your labs, for your projects if you want to, but you don't have to. As I said before, it's really, the purpose of this is going through the motion of making a board itself. So I won't grade the ingenious that goes into design of your board or how many sensors you have on there. I really don't care about that part. All I care about is that the schematic is clean, the board hopefully works, and that the layout is clean by itself. But it can be really simple and trivial. Yes?
Back on your schematic for the LEDs, in the video, you wire the ground into the MCU.
Yes, that's correct.
How does that work? Does the MCU ground or...
Exactly. So basically what happens is, what you do is the following. That's a very good question, actually. And I was thinking about it while I was talking about this. So what you do is, you have your microcontroller. You have an I/O line here, right? And then what you do is you have your LED, your resistor. Oops. Exactly not.
Yeah.
Go the other way around. So you have an I/O that goes resistor, LED, and then up to VCC. So what happens is that this I/O line that you have down here, if it's high, it's at VCC. So then this line here is at VCC, so we have VCC, VCC, there's no current flowing through it. When you pull this line down to ground, current will flow through this, sinking into the microcontroller. And usually microcontrollers are better at sinking current than providing current. So imagine you would do it the other way around, where you take an I/O line, go through the LED, and then out to ground. So now if you pull this line high, you will have current through here. So all the current that you're providing through this line has to actually go from the power line into the MCU and back out again. And they're most of the time worse at doing this than at sinking the current. Many microcontrollers these days can do both about at the same time. Others, they actually have special high power pins that can source more current than they can actually sink. So sometimes you really have to go into the schematics and actually read up on how much current can you sink or source. With the small little LEDs we're using, 10 milliamps, sinking is usually no problem. Yeah, good? All right. All right, next homework. This is after the schematic, once you make the PCBs, we will do the routing and actually making Gerbers. So the Gerbers are actually the files that you send off to the board house that they can then produce your boards with. So that's the Gerber files. They also usually include a drill file, which will tell them exactly what size of drill they will use at which point in your board to make a hole into it. They will then plate that hole so there's actually a connection through that hole itself. We will have a special lecture next Thursday, January 17th. I can't teach that lecture because I have some medical stuff that I have to take care of. But Enoch Lee will give a tutorial on PCB designs. He has been working on Altium Designer now for over a year and done some very incredible and difficult designs. So he is a good source if you have any questions or problems to ask. And he will give you a little design, like he will actually go through the motions of a design of making the PCB itself. It will be held in MEB 2555. That's a little classroom down on the second floor of MEB. It's nearby where the digital lab is, but the entrance, I think, is on a different side of the corridor, so you have to go and hunt for that one. There are not too many computers in there, but there are some, so try to team up and sit together. I guess if everybody is going, it will probably be a very busy class, but I hope it will work out. That's probably also a very good time of asking questions. If you have questions, I will try to have another couple of students there that can help you guys answer them and to get to the next step of making the PCBs. So the next part will be due on Tuesday, January 21st. So that's a week from Monday, if I'm not mistaken. All right, a couple of cool features. Once you actually go into the PCB design in Altium Designer, try to hit the 3 button. It will actually give you a nice 3D view of your PCB, so you get a good idea of how your PCB actually looks in reality. This was a PCB designed by another student. It uses the same microcontroller we are actually studying, the Smart Fusion here in the middle. And this is exactly the reason why we are not using the Smart Fusion for your schematic designs. As you can see, it's a fairly complex architecture around it to lay out this board. So this board has 6 different layers itself, so it has actually 6 layers that go through everything. It's a BGA part, so nothing that you can hand assemble easily. That's the reason you're not doing this. The board we are actually using for class is this guy here. This is the Microsemi Smart Fusion Evaluation Kit. As you can see again, this is the little part here in the middle, the Actel Smart Fusion. It has a microcontroller inside, a lot of peripherals, and an FPGA. It's all inside this package. Nice part about this board is it has a JTAG included in it, so you don't need to hook up any external device for this. It's just a USB cable that goes in here into your computer. Another USB cable actually down here for power. So this one is really just used for programming. This one here is used for power, and a USB to serial interface that you can use, so you can hook up hyperterminal to your microcontroller and actually get text in and out that you can use to do some behaviors with. It has a couple of different peripherals on board in addition, so it has a SPI flash memory. On the bottom side, there is an SD-RAM. It has an OLED display. It has a little potentiometer. Down here, it has an interface where we actually have an adapter board, a red one that plugs on the side into it. Be careful with these little pins here. They are very fine, and you can misalign the attachment board, so try to push them together properly so that they actually hold. You have a couple of push buttons and a couple of more pins for different switches and stuff like that. So in lab number 1, you actually will use these pins up here, not the big board on the bottom, but in later labs we will use the bigger board for more interfacing, more I/O capabilities. So I actually talked almost about everything on here. The Smart Fusion has a lot of different peripherals. It has a DMA to actually transfer stuff directly into memory from your peripherals without interactions of your microcontroller. We will talk about that later. Has UARTs, has an ADCs, has DACs, so we can actually interface with the physical environment and sample signals or actually produce signals. It uses USB for programming and has a USB to UART bridge. Has an Ethernet port on it, so you can actually hook this thing up right to a network if you want to. Has all the Ethernet PHY, and there are tutorials on how to actually get a TCP/IP stack and a little web server running on this device. And it has this mixed signal header. That's the guy down here. Okay. Sorry, this confuses me. We have 2 screens there. I have 2 screens here, and they're not exactly the same, but it's fun. All right. Software-wise, all the software, as I mentioned, is available online. The software that you're using to program the low-level stuff is called Microsemi Libero. So Libero is the software that programs the FPGA and configures your MSS. You will hear this short a lot. MSS stands for the Microcontroller Subsystem, MSS. So what do we see here? We have on the top left part where all your files are of your project. So as you can see, there are a lot of .v files in here. They are Verilog files. They get synthesized later on and put into the FPGA itself. On the right-hand side, you have the MSS configurator. This allows you to configure all the different modules that you're having in a visual way. So if you're familiar with Verilog, you know that you're writing little modules with inputs and outputs, and then you have a certain behavior with these inputs and outputs. Once you write this Verilog file, you drag it from up here into here. They pop up like a little block with all your input and output possibilities, and then you can draw on here with lines and hook them up to each other. In particular case, so we have the MSS, the microcontroller subsystem, which is actually a microcontroller itself, where you can configure clocks and inputs and outputs and all the peripherals that should be used, where they should be hooked up to. You can configure it to be a master on a bus. You have a bus itself and then an interface to a peripheral that you write in. It will be put into your FPGA that connects through the same bus as a slave. Don't worry, it is always complicated. You will learn all about it in the different labs. In addition to that, down here we have the design flow, which is nice. You can look at how you progress in the steps of actually programming your board. As you can see, it's a little bit complicated. It's not just like a one-time you write something and you hit the button and it programs it. It's actually first you have to configure the MSS. Next step is you have to synthesize your design. You then compile your design. You place and route your design. And then down here is actually the programming of your design onto the FPGA. The nice part about this software is it takes care of most of these steps for yourself if you hit this green run button up here. So once you make a little change, you hit the run button, you wait for 5 minutes, and the stuff is hopefully run by that time. On the microcontroller side, there's a different software package that's called Soft Console IDE. It's based on Eclipse, and this part is used where you program the C and the assembly for the microcontroller itself. So once you have the FPGA side and the MSS configured in microsemi, you switch over into soft console where you write C code or assembly code and get your system up and running. So this code is based on open tools. It's Eclipse. The debugger itself is based on GDB. You can do stepping. You can have register views. You can look at variables. You can actually look at the disassembled code that's produced by your compiler from your C code, which sometimes becomes very important when you're debugging stuff. As I mentioned before, all the tools are available in the digital lab, so they're pre-installed. You don't have to do anything there, but you can install all the tools on your computer if you want to. Go to this link or the shorts link like this. We'll give you a little tutorial on where to download the software. I have put it up on my servers here at the U, so if you're on campus with your laptop, it will be a very fast download, and we won't overload the university network because it's about a 1.2 gigabyte download or something like that. And then there, in the tutorial, it mentions how you can get a license so you can install it and run it all on your computer. Any questions so far with the lab? They start next week, so Monday is the first lab. No? All right. Quick review of what we did last time. So what distinguishes embedded systems? We talked about this list that we had over here. And there are a couple of other points that I forgot to mention. So they are usually application specific. We mentioned that one. They're not general purpose. They are usually made for a specific application. They are resource constrained. Most of the time you only have the resources that you really, really need for this application to run, and not just gigabytes of memory or RAM. And they're sometimes real time. So they have to get an input and in real time reply to this particular input or react on a certain control system. And one of the things that we actually haven't mentioned last time, they run forever. An embedded system doesn't really start or stop. Once it starts, it hopefully runs forever until it crashes, right? And hopefully that doesn't happen. And once it crashes, what I have to do is hit the reset button or take the power cord out and put it back in. But that's one of the important things about embedded systems, they run forever. Technology scaling is driving the embedded everywhere. So that's exactly what we had in the minute quiz itself. More particular, this changes for microprocessors. We have memory that gets bigger and cheaper and lower power, imagers, MEMS, kind of sensors, accelerometers, gyroscopes, etc. that help us with power. And we have better energy storage and better energy generation itself, so energy harvesting. So we answered this question a little bit last time, but I want you to get together in groups of 2 or 3, quickly discuss on why do we study, again, FPGAs, and why do we study the MPU32? So why do we study this ARM microcontroller that we're using in the labs? All right, 1 minute. Ine, you should switch. Okay, so why do we study an FPGA? I mean, we thought this is an embedded systems class, right? So why FPGAs? Yeah.
It's a very flexible system. You can make a small amount of FPGAs for reasonable.
Okay. Yes.
Based on high-level language like C.
The FPGA? No, FPGA is very low level. Very, very low. Yes.
Basically, you can do your own chip design.
Exactly. Yeah, that's key. You can do your own chip design on the chip without having to spend $5,000 for a run and then knowing that the chip doesn't work and you have to wait another 3 months for the next chip iteration that actually happens. So the FPGA actually allows us to really go down into the detail of how a microcontroller works by actually going and looking at the details of how bus transfer works, how these signals going out from microcontroller into your into your peripherals that you're writing. Why the MPU32? Should be a fairly easy one by now. Yeah?
Everybody does what we need. A lot of big companies use it.
Exactly. A lot of big companies use the same core. So by starting this one particular core, you have a huge choice of different microcontrollers that are becoming available. Okay, so now we start actually the meat of this lecture, and we're going to start looking at the architecture of this MPU32. So in the context of computers, what does architecture really mean? Where have you guys heard architecture in computers before? Sorry? Ever heard architecture? Yes?
So like we studied MIPS and x86, so these are different instructions.
It's one of the architectures, yeah. If you actually look into it, with respect to in computers, the architecture has a lot of different meanings. It can be sometimes very confusing. So, for example, computer organization or microarchitecture itself. You had a class actually called Computer Organization and Design, I think. I think it's even a prerequisite for this class. So you have heard architecture before. It talks about the control data paths, pipelining, cache designs of systems, et cetera, et cetera. So that's computer organization. It can be used in system design or platform architecture. So there we talk about what kind of memory design, I/O designs do you have, what memory controllers are you using, do you have a DMA or not. So that's more the system on chip kind of design architecture. And then there's the instruction set architecture. That's more what he said. So what is the ISA? Exactly. Well, in 1964, IBM introduced the 360, or the IBM 360, and there the definition of the ISA was an instruction set architecture is the structure of a computer that a machine language programmer or a compiler must understand to write a correct timing-independent program for that machine. Which word do you guys think is key in here? This whole sentence. Like which particular word describes the ISA best? Construction? Machine language? Where is it? Wait. Okay. Never mind about that. It's basically a contract between the programmer and the machine, right? Understand, yeah, kind of. But for some reason, I had the idea that there's contract in this word. That's how I memorized it yesterday. So it's a contract, right? Basically, an ISA tells you what you have to write and tells you how the machine will interpret what you write in your code. And you'll make sure that the machine really does that and not something else. So that's what the ISA is about. There are a couple of major elements to an ISA. We have, on one hand, the register set. On the other hand, we have the memory architecture. In our case, they're both 32-bit, and they can vary for different microcontroller architectures. So sometimes they're 16-bit or 8-bit or a mix of multiple different ones. The endianness is important, and we'll talk about endianness next time, in the next lecture. In our particular case, we have several different registers and one weird register that's a little bit outside that we will look at in a second. If you actually look at this register in particular, it's not just like to store information, but it has certain bits that mean very particular and specific things. And we will look at that in detail. We have the language that you're writing. So in this case, this is ARM assembly code, where things refer to different major elements. So for example, we have registers that we tell to do things. We have locations in memory, so they are mapped into the memory map to do something over there. We have functions that react on these special registers, bits that we have down here. We will talk about them in detail. And we have certain logos or labels that will tell us and refer to something inside our memory map. So for example, what this particular thing here does, this is a move where it will tell that we want to write 1 into this register. This is a load instruction telling us to load something from a memory location into register 1. This is a branch instruction. Basically, this will change the PC, the program counter, and set it to loop if a certain condition happens. And down here we have a subtract operation where we will subtract 1 from a register that's in here. So that's the whole thing. That's the ISA. That will tell us what to do, what the machine will start executing, and what to do with memory allocation and shuffle the things around themselves. So there it is, a contract between architecture and programmers. I knew I had it somewhere on the slide. The major elements are the register set, very important. We have the instruction set itself, so that will talk about addressing modes, word size, data formatting, operating modes, and conditional codes. And we have the calling convention, which is not exactly inside of the ISA. So this is usually actually a part of the application binary interface. Basically, a compiler has to adhere to the ABI in order to do and write code properly. But oftentimes the ISA helps you with this ABI itself. So there are features inside the ISA that make the ABI easier to understand or has certain operations to make it a lot faster. ARM is a fairly old architecture, actually. Went through a lot of different generations until we came to the situation that we have now. We had the ARM 4T, the 5TE, the 6, and the ARM 7s. In the ARM 7, that's where we are today. We have 3 different categories. We have the applications, the real-time, and the microcontroller ones. Looking at this in more detail, so we have the Cortex-A's, which are the application processors that they're having, the Cortex-R's, which are their real-time microcontrollers for real-time applications, the Cortex-M's for microcontrollers, and in addition to that, they have something that they call the secure core. I've never used them. I don't actually really know what they are. And just recently, they added 2 more up here. They're also application processors, but these 2 are the new 64-bit ARM architectures. All the other ones, certainly down to here, are 32-bit. The one that we are looking at is the Cortex-M3. It's the middle of the line of the microcontroller ones. We choose that one because it's available on a lot of different platforms. It gives you a good overview of everything that's actually inside of here. It doesn't give you much on the Cortex-R's or the Cortex-A's, but they're also a lot more difficult to understand. But hopefully by understanding the M series, you can start and go out and learn what the A series does. So what does the Cortex-M3 ISA contain? Well, we have instruction sets we will talk a lot about. So this is the assembly code language, which will come up in a second. We have the register set, and we have the address space. So the register set looks as follows. It's a zoom into this whole thing, where we have the lower registers R0 through R7, so 8 lower registers. We then have the higher registers R8 through R12, and then we have a couple of special purpose registers. R13 is the stack pointer. Be careful, there are 2 stack pointers. Depending on the mode your microcontroller is actually running in, the stack pointer can be replaced. This can be used for safety reasons. We have the link register, the program counter, and the program status register. The other part is the address space. Since we have 32-bit of addressing, so we can address 2 to the 32 bytes, which makes 4.2 gigabytes of memory that we can actually address on a microcontroller, no matter which one of the Cortex's M3 series that you're using. But this address space is actually partitioned into a lot of different subparts. So what you can see is we have something that's called the code space. We have something that's usually the RAM space, where you have RAM memory. You have the peripherals that are sitting somewhere in the memory, and we will look into that later on when we talk about memory mapped I/O. You can have external memory that you can talk to, more external memory, private peripheral buses, more private peripheral buses for external off-chip system things, and a system memory map. We will look into several of these different things later on in the lecture. Instruction set encoding, and we're going to spend a little bit of time on this now. This looks kind of scary, right? So what does this instruction set encoding really do? And once you actually look at this and understand it, it's really not that hard. Think about it this way. Your code that you're writing gets compiled into a binary stream, right? And then put into your microcontroller somewhere in its memory. And all it does is it goes, reads a line, decodes what this is doing, does the operation, and then goes to the next line or jumps to a different line to read a certain byte or word out of the memory again. So we have to have some sort of mapping between what you're writing in assembly to opcodes or bits and bytes. And that's what these things are doing. So this information gives you the mapping between the opcodes and the assembly language. So that if you actually get a binary itself, you could go in there and actually start decoding the whole thing and actually figure out what the assembly is doing. So that's what a disassembler is doing. It looks at the binary code and then puts you into words of what's actually standing there for a little bit more readable purposes. So what does it do? So for example, in this case, we have the add instruction. So you want to add something to a register. It has 4 different encoding types. So there are 4 different add instructions. Actually, there are a lot more. These are just 4 example ones. For example, up here, what we have is we have the add with a condition, a register for where we put something in, a register where we take something out, and a immediate value. This is the assembly language. And what happens is this will be put into an opcode that looks like this. So in this case, as you can see, it's a 16-bit opcode. It will be 0001110. That's always the same for all of the different combinations that you can have in here. This immediate value will be stored in the bits 6 to 8. This register in 3 to 5, and this register in 0 to 2. Right? Remember, you have 16 total registers. We have 3 bits. How does that work? Yes, you can only access the lower 8 registers. So what do we do if we want to access another one? One of the higher ones. Exactly, right? So the key here is ARM language, the ARM ISA is actually dynamic. So sometimes you can have 16 bits for an encoding. Sometimes you can have 32 bits for an encoding. Of course, if you use only 16 bits, you can have 2 instructions in one 32-bit word. Makes the whole thing a lot faster because you have one memory access, you read 32 bits out, and have 2 instructions that you can start executing immediately. Instead of just having to go one by one by one. It speeds up things, uses less memory space, etc., etc. But of course, you have to have some sacrifice in this case. So if you want to use a higher bit register, you have to go to this encoding here. As you can see down here, we now have the RN and the RD going from 8 to 11 and from 0 to 3 on the higher word itself. So now you can actually address all 16 of them. Make sense so far? Yeah? Okay. If you want to know all of the different possibilities, go and look at the ARM v7m Architecture Reference Manual, also called the ARM. It's linked on from the website, and you will actually use this a lot in homework number 2 later on, where we have some exercises in going from one way to the other and back again. Why do we do this? Well, sometimes compilers make mistakes, and you actually have to go and look into your disassembled thing to figure out what's going on. Sometimes even go into the opcode to see if that stuff actually worked, did the assembly work properly. Sometimes there are very stupid mistakes or very difficult to find, but it's a good way of actually understanding what's really going on underneath of the whole thing. So add is only one of the functions that's possible in the ISA. There are a lot of different ones. One of them is branch instructions. So branch instructions will basically set the program counter to a certain memory location. And there are a lot of different branches that you can do. Some of them can only jump a certain memory limit. So for example, if you just have a B branching instruction, you can jump plus or minus 1 megabyte from where the program counter sits right now. You have a lot of different ones. You can have a BL, so that's a branch and link function. That one will jump to a subroutine and do something with the link register that we will look at later on. You have a BLX. This can jump anywhere in your memory space. So more or less, what's the difference between these two? Why is there a function that's BL that can go plus minus 16 megabytes and a BLX that can jump anywhere? How can you even jump to anywhere in the memory? What do you guys think? So think about it this way. You have 32 bits, right? You have to somehow encode the instruction you want to execute and the location that it should go to. It has to all fit in 32 bits. Yes. BLX uses a register, go and reads the value of the registers and jumps to that location, while BL is directly encoded in the instruction itself and doesn't need a register. So that way you can jump up to 16 megabytes, but not more. There are, of course, instructions for data processing. I mean, that's the main point of a microcontroller, right? You want to add, you want to subtract, you want to multiply. There are a lot of different instructions. There are, yes?
Sorry, just on that last side, it says TLX optionally change instruction set? Did you
Yes.
address that already?
No, I have not addressed that yet. ARMs can run in two different instructions. So they can run either in thumb or thumb2, I think, is it? If I'm not mistaken. They're two different instruction set encodings. Now the Cortex M3 only can run thumb2. So it cannot switch its instruction set in the jump itself. And if you actually do a switch, you will get a hard fault and you will be stuck forever. So it will crash, basically. It will not allow you to jump into a different instruction set. The way of doing it will come later on. It's by setting the last bit to a 1 or a 0 of the jump address. Since you can only jump to 4-byte increments, the last 2 bits are actually used for encoding of what you want to do. And sometimes you can jump to a certain address and switch the instruction set at the same time. That way, for example, the A application processors, they can have mixed binaries of thumb and thumb2, and they can be mixed in together. And by jumping into a different function, you can switch into thumb and then back into thumb2 without any problems and very quickly by just having different jump addresses.
You can slow down the arm too. They'll run full arm instructions too.
Yes. It's actually between the arm and thumb jumping differently,
Yeah.
if I'm not mistaken.
That's right.
But we will look at that later on when we talk more about memories. Yes?
Okay, well, what's the advantage of continuous instruction?
History. It's just how it developed. It's first came the ARM architecture, then came thumb, then came thumb2, and later on they realized, well, we have to have somehow a way of merging them together. And I think later on we will have a slide that will show you the advantages of using a different language. Thumb2 has this mix between 16-bit and 32-bit, which is new, so you can really optimize your code and make the code base smaller. Very important for microcontrollers, not as important for application controllers themselves. Yes?
Is this probably a trend we're going to see with the new 64-bit microcontrollers?
No, this was a lot earlier. This happened a lot earlier.
Do you
But
think they'll do this though, where you can jump between?
most likely, yes. Most likely. I have not looked at the 64-bit architecture yet at all. Maybe that's something a grad student actually wants to pick up. It would be a good topic. All right, data processing. So all adding, ANDing, counting bits in your registers, it's all in data processing instructions, and there are a lot more. Look at the ARM architecture reference manual. Same for load and store instructions. Load and stores are used to get stuff out from memory into registers and from registers into memory itself. There are a couple of miscellaneous instructions that don't really fit into a bigger category. We will look at some of them. Most of them we won't look at, but they're sometimes interesting to look at. But other ones that are really important is wait for event and wait for interrupt. We will look at both of these instructions when we talk about interrupts and how interrupts are handled in your microcontroller. Okay. Next is one of the things that's a little bit complicated and sometimes confusing. If you actually look at ARM assembly, you have an addressing mode that you can use. So if you want to address something in main memory, there are 3 different ways of doing this. There is the offset addressing, pre-indexed addressing, and post-indexed addressing. And they all have different behaviors on how a register gets changed or how stuff gets taken out of memory and put into registers or vice versa. So offset addressing is when you say you have a register and an offset to it. So the load or the store instruction will go and get that memory address. So it will take the base of the register, add whatever is in the offset to that base address, and get that out of memory. But it won't change the register itself. Pre-indexed addressing, so when you add an exclamation mark at the end, it will actually first apply this offset, store it in the register, and then take that value and go that and get it and do something with it, or store something into that particular memory address. And the last one is where you have a register and an offset. Here it will actually do the operation on the register memory location and then apply the offset to that particular register. Why do you guys think that we have these encodings? Can you see an advantage of one of them, or when would you use one encoding like this instead of this, or vice versa, or maybe this instead of this?
Timing stuff.
Timing stuff?
Translation directly from C.
Yes. Have you ever traversed through an array? If you think about it, what happens in there, oftentimes you have an incrementer that just jumps from one memory location to the next, to the next, to the next, right? So what you can do is you can use this one here, and in one instruction set, go read the memory location After reading it, it will add automatically your offset to that memory location, and it will point directly to the next location in your array, all in one instruction set. Instead of having two instructions where you have to load it from memory and then add to the register 4, for example, or whatever the offset in your array is, right? Again, it's all about making it compact and very dynamic language. But it can, of course, it comes at the disadvantage of making everything more complicated. If you actually read assembly code, sometimes you have to think about, okay, what indexing happens and what really happens here now. But that's the 3 different addressing modes. So some examples for the offset itself. Offset can be binaries, numbers. So for example, here this is an offset 10. Index registers are usually marked as RM. You can have a shift in your offset itself. So here, the offset is stored in a register and left shifted by a certain amount of bits. And there are a lot other more weird options. Makes the whole thing even more complicated. But you won't see that many different ones. So most of the time, you see one of these different types. Sometimes you see a left shift because that's just very convenient, left shifting something into a register to get more compact and different notations. There's an other thing, and that's called the immediate constants that can be set on on one of your codes. So again, I'm trying to help you here to read this architecture manual, because what you will see in there are a lot of these different tables with a lot of different encodings, and then you have to understand, okay, what does this now mean? You have to decode of what the different bits and bytes mean inside of a function. This is another one of these things that will break your head for a little while until you really understand the concept. So what it is it's an encoding that's dispersed through your opcode. So you have the I bit here, you have an immediate value, and then you have an A, B, C, D, E, F, G, H back here. And the decoding is as follows. You have I immediate 3A, that's these bits here, and then this will produce the constant described as follows. So if you look at it, you have the I as a 0, and then down here it becomes the 1. Immediate 3 are always the middle 3 ones, and then the A, so that's the first one up here, will determine of what type of constant it is, but sometimes also appear inside of the constant itself. Right. It's a very complex kind of encoding, decoding that you have to do. But again, it's all about making stuff small. How can we fit big 32-bit constants into our opcode without having to go and operate on registers themselves, because that's sometimes always another step, or it's more complicated to do, or takes more time. Yes?
So is what that's saying is it's using the I, the 10th bit, the immediate from the 14th down to the 11th bit, and then the 8th and the 7th bit?
Yes.
To do the encoding.
So one little note here. As you can see, it's actually partitioned into 0 to 15, again 0 to 15. So that's 0 to 32. It's 2 half words. So in total, it's one 32-bit word that gets read. It's just how they write it into 2 different parts, because sometimes you can have 16-bit, sometimes 32-bit operators. Any questions so far on opcodes and decoding and encoding? No?
Sorry.
Yeah? Please
The-
ask questions. I mean, now is the time.
So for the processor to know which, if it's doing a 16 or a 32,
Mhm.
is that in the upper 15?
Yes.
Some of it?
There are a couple of keywords up in here that will tell you if it's a 16 or a 32-bit operation. Yes. And that way he knows, is it 2 operations or is it 1 opcode that I have to decode? Yes. Yeah.
Immediate 3 is like 11, 12, 13, right?
It's 12, 13, 14, actually. Yeah. Of the lower half word.
A 7.
0 to 7, yeah. And then 15 here, and then 0 to 9. Bit 10 is the I in there. Everybody confused yet? It will hopefully get more clear once you start reading some of these instructions and actually doing it manually in the homework itself. Okay. Let's look at this application program status register, because that thing is actually really important. And that's a register that tells you what's going on in your system, what the results are of some of your opcodes that you have been doing. In particular, the bits 31, 30, 29, 28, 27. These are the indicators of a result of your instructions. So what do they mean? Well, the n bit is a negative conditional flag, so it will tell you if the result of your operation was negative. The z is a 0 condition. It will be 1 if the result was 0. Very logic, right? Z is the carry condition, so this will indicate 1 if the carry bit has been set. V is set if there has an overflow happened, and Q is used in two of these special functions. It's the signed saturation function and the unsigned saturation function, else the Q bit is not used. So how do you update the application program status register? Not every instruction actually updates this register. More particular, if you have a subtract Rx, Ry, Rx will be equal to Rx minus Ry, the APSR will be unchanged. This will not affect the APSR register. But if you add the little s at the end of your instruction, the APSR will be updated. Similar for add Rx, Ry will not impact the APSR. Add s updates the status register. Yes?
Why would you not want to update it?
Sometimes you don't. Sometimes you don't care about it. Or sometimes you actually have a result, you do an operation, and it only then check for what the APSR was up above to do something else. Yeah?
So why is the first one, APSR will be unchanged? Because what if you have a negative result?
Then you miss it. Or it gets lost. It oftentimes, so that's now the compiler, either your job as a programmer to say, well, I want to check on the negative result. After this, I want to check, has the result been negative or 0, for example. So you have to use the sub s function. But if it never gets checked, you don't have to use the s conditional. And if I'm not mistaken, then the s one is actually a 32-bit instruction, while the sub one is not, if I'm not mistaken. But I have to look at the encoding itself again. Yes?
Will it overflow then?
Yeah, absolutely. Absolutely. It overflows. It does everything. The functions do the exact same thing, except one of them updates the APSR, the other one doesn't. But else the result will be exactly the same thing. So now we update this APSR. How can we use this? Well, ARM has this really neat little thing that's called conditional execution. Conditional execution allows you to execute a certain function based on the status of the APSR. And almost all of the assembly language functions have this conditional execution option. So what does that mean? If we have, for example, a add EQ, this add operation will only be executed if z is equal to 1 in our code right now. So really handy, right? So instead of having a branch into somewhere where you have this or keep going executing, you can have just this one function as an add equal. Or you can add an NE, CS, or all these different options back here, which will operate on the different conditional flags in the APSR. Of course, we also have the branch instruction, so you can conditionally branch to a different function or somewhere in your memory. But sometimes it's only just 1 or 2 functions that you actually want to have conditional, and that way you can use it in a way more efficient way. Yes?
Do you just depend it onto your instruction?
Yep.
So you say like add.
Just add any.
Okay.
Not all of them have it, but most of them. Okay. As I mentioned in the beginning, there is no official book for this class, and this is the reason. There is a lot of material online that we will cover in this class, and all of these things are available for free. There is the ARM that we talked about a lot. Really have a look at this. It's a huge document, but everything is described in detail in there. If you need to know something about the instruction set or the opcodes, it's explained in there. Cortex-M3 technical reference manual will explain you particularities about the Cortex-M3. We have the ARM procedure call instructions. So how do we make procedure calls? We will talk about that later, how C procedures work. We have Actel has Actel or Microsemi, it's the same company. Actel got acquired by Microsemi, so that's why you will see both of them interchangeably. Actel has the microcontroller subsystem user's guide, which will explain everything about the MSS that we will be using. Smart Fusion Evaluation Kit is a user guide to the kit that you're using, the hardware itself. There is a program analog user guide, so how do you program the analog part of your Smart Fusion. Plus, there is more code sorcery, which is the basis underneath the open source tools that are used for the C side. There is documentation on all of their stuff. There is documentation on the assembler that's used, the GNU AS. There's documentation on GCC. There's documentation on the linker, utilities, and the debugger itself. All the documentation is out there, free for you to go and look at. It's probably thousands and thousands of pages, and no book can really capture everything together. This book here does a really good job in getting the gist and the big parts together, explaining it in words. I encourage you to look at it if you want to. I have 2 or 3 copies that you can borrow for a little while and look at, and purchase the book if you are interested in it. But there is no real book that you can follow and get everything. Especially these documents change monthly, and so you want the latest documents themselves. Okay, we have about 10 to 20 more minutes. So let's do a little exercise so I can explain you of what's going on here. This is a typical ARM assembly code that you would see. Like you probably have seen ARM before, assembly before. Some of the things are very typical. You have labels, right? And then you have the instructions back here that do something with the labels. So you have this quick reference guide, right? That you had, the quick ref guide. So try to be in groups of 2 or 3. Try to decode and see what this is doing. More specifically, try to figure out what is the value of R2 if you get down here to done. And if you have questions, please flag me down and I can come and help. Did you guys solve it? Not yet? Solve? You think so? All right, let's try to solve this. What happens? Move S R0 1. So we move 1 into R0. S indicates we update the APSR. What happens?
The negative, the 0, and the carry flags get set. I don't know.
Carry flag gets set? Why?
That's what this says. Oh, that's on
Why would you set the carry flag? The carry flag happens when you have an overflow in an add, unsigned add, right? If it overflows, then the carry bit gets set. Right. So z equals 0 still. Move s r1, 1, same thing, right? Z equals 0. Move s r2, 1, so r0, r1, r2 is now 1. Z is equal to 0. Sub r0, r1, what's the result, or what happens with r0? 0. So what happens? The APSR? Why? No update. Exactly. There's no S here. Z is equal still 0. Branch if not equal. So Z is still 0. So we take the branch. We jump down here. This will never be executed. The solution is on the slides too, if you want to look at it again. All right, so how would this now look in reality? Right, what we saw there is just an example ARM assembly was the right language. But in reality, in a file that you write in assembly language, there's a couple of more things that you have to actually specify in your assembly files. These are not ARM assembly instructions, but they are for the linker and the assembler itself, given information of what's really going on. So what we have is up here, we have these dot notations. You will see them, and we will talk about them more in details, but they basically give information to the linker. In particular, the equal will set this variable to this number. So in this particular case, this is the stack pointer that will be initialized to a certain RAM memory location. It then will say that this is the text section. We will talk about that later. The syntax is the unified syntax. So there are several different notations and syntaxes that you can use in your assembly files. This one here is the unified version. We want to write thumb code. So we have to tell the assembler this is thumb code that you're writing. And we tell it that the .global is _start. So what do you guys think does this do? What will it tell to the linker?
Program starts.
Exactly. We will see how this really happens in reality, but this basically tells the linker that, hey, you should really start execution at _start. And _start is a label inside of our text section somewhere. So the linker will know, okay, start is pointing to this first thing here, and that's where we will start our execution. And then it says that .type start is a function, so that we know that this is a function type for the ABI to do specific things. In addition to that, we have an _start is a word, so the first line is actually the stack pointer, and the second line is the start symbol. We will see what this really means. In reality, what it actually means is that the initialization vector, the first location is always the stack pointer. The second one is the first jump location where the PC will be set to. So at boot up, it will read the stack pointer out of the first memory location it gets to, the first jump address out of the second register, and then execution starts over here. And as this is an embedded system, at the very end we have a dead loop. It will never stop executing. We will never get to the .end because here it will just keep dead looping. It's spinning forever. Yes?
The things that you get from here are like assembler directions, right?
Yes.
So how do those turn into instructions? How does that
They don't. The assembler uses them to do stuff. Or more particularly, the linker is actually going and using some of these information to get certain memory locations and replacing stuff with it. But we will look at that in detail. So getting this now into a binary, these are the different code things. This is actually a make file. If you write this make file, take the assembly code that we had over here, store it in a file called example1.s, and at the end you will get a binary out that you could program your microcontroller with, and you could start executing it. It's more as a reference here. You will do this actually all in lab 2, if I'm not mistaken. All right. That's it for today.